In this section, we're going to take a look at the mean and the standard deviation of a binomial probability distribution. And you may remember from a couple discussions ago that for any discrete probability distribution, the mean, which represents the expected value, is given by the sum of x times p of x, right, where x is the value, the data value, and the p of x is the probability of that value. And then we also had this one, although we didn't use it because we had the calculator computed. But it is this. The standard deviation is the sum of these differences. X minus mu, the data value minus the mean, squared times the probability. Square root of all that. Well, as it turns out, for a binomial distribution, these formulas simplify to these. So the mean is equal to simply n times p, where n, that's the number of trials, and p is the probability of success on a single trial, and sigma is just the square root of n p q. Right, so this is the mean, and that is also the expected value. So that's the value we would expect when we run an experiment. And this is the standard deviation. So here's a simple example of how to use these formulas. So let's find the expected value and the standard deviation of a binomial experiment where there's going to be 8 trials and the probability of success on a single trial is 0.20. All right, so the mean is the expected value, and that's just n times p. So in our case, n is 8, p is 0.2 or 0.20, so we're going to get 1.6. Now see if that makes any sense. Just intuitively, you're going to do something 8 times, and there's a 20% chance something's going to happen. So 20% of those 8 times is what we would expect for that something. So 20% of 8 is 1.6. So the formula tends to make some intuitive sense. And sigma, standard deviation, is the square root of n p q. So for us, it's going to be the square root of 8 times 0.2, right? We just did that one. That was actually 1.6. We could just type in 1.6, but let's show all of it. And then q, now q, look at this up here. P is 0.2, so q is 1 minus p, right? This is the probability of success, 20% chance of success, so there must be a 1 minus 20%, 80% chance of failure. So this is going to be a 0.8. Now, I'm going to do this on the calculator. So what I'm going to do is I'm going to press second, and then I'm going to hit down here a little ways, right? I'm going to hit the x squared key, and what that gives me is a square root, like this. And then I type in the 8, maybe the times key, or parentheses if you like, 0.2 times 0.8, and as you do that, the square root follows it over, and then I press enter, and this comes out to be 1.131370085 on my calculator. But remember, we're going to round here, so I'm going to round this to one place more than my data values. But see, I don't really know the data values, so I'm going to round this since, let's see, what did we get here? I got 1.6 here. I think I'll just round it to 1 decimal place. So sigma, I'm going to say is 1.3, right? So mu, the expected value is 1.6, standard deviation, 1.3. Okay, so we've got these values, 1.6 and 1.3. What does this mean? What does this mean? This is the expected value. So I wrote it here. Let's look at it. It says, here's what this means. If we were to repeat this experiment many times, right, many squared, many times, like either we do it ourselves or maybe we have lots of people in different places doing it. What's the experiment? well, we don't know exactly what this experiment is, but there's 8 trials. So we do this thing where we take 8 trials at this percentage of success. So we do this experiment many, many times, and every time we do it, we record the number of successes. Then we take the average of all those successes. So like in trial 1, 2, 3, 4, 5, trial 100, trial 1,000, we find the number of successes, and then we average all those. Well, that average is going to be a number close to 1.6. So on the average, we expect about 1.6 successes in a trial. And of course, we can't get 1.6 successes in any trial, but this is an average, remember? Now, let's just talk quickly here about unusual values for successes. So for a binomial distribution, it's unusual for the number of successes to be really high or really low. By high and low, we mean this: the expected value plus 2.5 standard deviations, or lower than the expected value minus 2.5 standard deviations. So for example, in that last problem that we just did, here's what we got. We got the mean is 1.6 and the standard deviation is 1.3. So that means that it would be unusual to get more than, all right, here we go, mu plus 2.5 sigma. So now what we're going to have is actually, let me get the numbers right here, 1.6 plus 2.5 times sigma, which is 1.3, which turns out to be 4.85 successes. So it would be unusual in this kind of an experiment where, remember what we had here? We had this. I'll do it right here. We had 8 trials, and the probability of success on a single trial was 0.20. All right, so in this case, in whatever this experiment this was, it would be unusual to get more than 4.85 successes, right? Because the expected value is 1.6. Now, it would be unusual to get more than this many, or less than, or you know what, I'm going to say fewer than. Now this is mu minus 2.5 sigma. That's going to be 1.6 minus 2.5 times 1.3. And that turns out to be negative 1.65, which of course is not possible. You can't have a negative number of successes, so we don't have to worry about that one. All right, so that's what we mean by something, some number of successes being unusual. So if this is what you're expecting, 1.6, and then you get something greater than, say, 4, say somebody tells you, oh, I got 6 successes here, that would be suspicious. Ooh, let's look at another example. Here's one. Do you tailgate the car in front of you? About 35% of all drivers will tailgate before passing, thinking that they can make the car in front of them go faster. Right? So there's a source for this. We've seen that source before in this Bernice's book, Are You Normal? Okay, so here's what we know. About 35% of all drivers tailgate before they pass, thinking they can make that driver speed up. All right, now, suppose you're driving a considerable distance on a 2-lane highway and are passed by 12 vehicles. Okay, so let's write some of this down here. So we know right up that n is equal to 12. There's 12 trials, right? You've got 12 cars. And what are we counting here? R, the number of successes. That's the number of vehicles that tailgate before passing. All right, so make a histogram. What will compute the expected number of vehicles that will tailgate? So we're counting the number of successes being tailgating. So we're going to let P, now that's going to be the probability of success, and the success is seeing somebody who's tailgating. So that's going to be 3.5. So then automatically what is Q? 1 minus 0.35, which is 0.65. All right, now what have we got here? You know, I'm not going to make a histogram with all these bars. Let's just go down here to part B. Part B says this. Compute the expected number of vehicles out of 12 that will tailgate. All right, so the expected number, we have a formula for that. Mu is n times P. So the expected number is n, which is 12, times P, which is 0.35, and I got that to be 4.2. All right, so we're saying the expected number of, so we're saying the expected number of vehicles out of 12 that will tailgate is 4.2. Now keep in mind that 4.2 is an average. So like if you were doing this where you were what? Suppose you're driving a considerable distance and you do this, you get passed by 12 vehicles. Okay, now you do it once, then you do it again, then you do it again. You do it many, many times. So on the average, how many vehicles would be tailgating? So on the average, it would be about 4.2. And then we're also supposed to compute the standard deviation. So how about sigma? That's the square root of NPQ. Now look, we've already got N times P, right? We just did that right there. So that is, how about if we do 4.2 times 0.65 and take that square root. So I'm going to press the second key. I'll go down a ways, press that x squared key. It's got the square root on top, so I get the square root, and then I put in 4.2 times 0.65, and that square root moves over. And when I got this, I got 1.65227, bunch of other stuff. I'm going to round this off. So I'm going to say sigma is, now I'm reporting the mean to one decimal place. I'm going to report this to one decimal place. So I'm going to round off to the 6. But I look over here, that's a 5. Now remember, in statistics, you round to an even digit. That's already even. So I'm just going to keep this as 1.6.